Hello everybody, my name is Hubert Schneegans and I am a scientific assistant at Instant Lab EPFL. In this presentation I will present our submitted paper, Statically and Dynamically Balanced Oscillator based on Watt's Linkage. So in 2014 we introduced the concept of 2 degrees of freedom oscillator as a promising candidate to replace the traditional 1 degrees of freedom spiral oscillator that are in most of the mechanical timekeepers. This 2 degrees of freedom oscillator allows us to simplify the escapement mechanism whose efficiency problem has been stagnated for several decades. Indeed, with the use of such a structure, the complex escapement mechanism is removed and can easily be replaced by a crank driving a pin fixed to the oscillator. This one can gain or lose amplitude without changing its frequency as the driving crank torque varies. So there are several ways to create a 2 degrees of freedom oscillator. Here we chose to design one coupling in parallel at 90 degrees to 1 degrees of freedom oscillators. And I encourage the viewers to see our 2 first references of the concerned paper if they are interested in some different kinematics. Through this presentation we will focus on the chosen structure of the 1 degrees of freedom oscillator that will compose our final 2 degrees of freedom oscillator. More particularly, we will see what kind of constraint this oscillator should overcome and see how we will design it for this purpose. So we decided to base our 1 degrees of freedom oscillator on the 4-bar linkage found by James Watt. This linkage was invented by him to convert circular motion into roughly linear motion in order to drive the piston of a steam engine. Each orthogonally coupled linear oscillator of the previous slide moves in a straight line, so will be a Watt oscillator in our new mechanism. The structure has some interesting inertial characteristics that will be discussed later. In the field of mechanics, and more particularly in horology, oscillators are expected to remain at the same frequency regardless of external disturbances. Temperature changes that affect certain materials, changing their inertia or their stiffness could be one of them. But here we will focus on another source, which are the external acceleration that could be linear or angular. The best known is gravity, which is static, and the dynamic ones could appear if, for example, the frame of the oscillator is subjected to any linear or angular accelerations, like, for example, wrist motion. If the oscillator structure is not correctly balanced, the static or dynamic accelerations could affect its oscillating motion by slowing down or speeding up its period. And after several cycles, the displayed time will not more be correct. So to find an appropriate solution for oscillator, we decided to model the Watt oscillator to understand how its mass should be distributed to make it acceleration insensitive. As the purpose of this oscillator is to be one day implemented into a watch, its frequency must also be tunable to fit technical specification. As the Watt oscillator will be manufactured with flexure elements, we developed a pseudo-rigid body model to get as close as possible to his behavior. We can see our Watt oscillator is composed of 3 rigid bodies, 2 levers, x1 and x2, here and here, and a connecting bar named Watt bar x, here. To simplify our model, we made several hypotheses. So all the solids are considered infinitely rigid, having their proper mass and inertia. For each solid we define its center of mass, Ex1, here Ex2 and Ex3, using in our paper cylindrical coordinates. All the bodies are supposed to be connected to each other by means of frictionless revolutions coupled with torsional spring here, here, here and here. In our work, we are considering a planar problem. Then we will only treat the in-plane effects of gravity and other linear or angular accelerations. And our last assumption is that we considered small angles for the resolution of our problem. So to be able to balance or tune the frequency of our oscillating structure, we can modify several inputs, which are the location of the center of mass of the lever x1 and x2, as well as their inertia. So as the Watt oscillator is a flexure mechanism, we translated into its abstract linear mass spring equivalent representation by solving its static and dynamic equations. This will help us to highlight the different contribution of the linear acceleration, such as gravity, on the resulting forces and stiffnesses. In parallel, we created on COMSOL multiphysics a simple watt oscillator on which will be tested our analytical results. So we can see the global architecture of it, with its two main levers composed of rigid bars and counterweights that you can see here. This is one solid, and here this is another one. And we also have the rigid watt bar X having its center of mass slightly shifted thanks to a small unbalanced mass. So this is again one part here. So in our static study, one can see gravity acceleration will affect both the resulting force and stiffness of the equivalent model of the watt oscillator. The main effect will be a resulting sag of the oscillator made visible by the unwanted displacement of the watt bar X. Also, we will have a stiffness variation, and this one could be measured by its frequency variation. So we will try first to cancel the sag of our oscillator, because we found out that if this one is too significant, we cannot predict correctly the frequency variation of the oscillator, as our model is only valid close to its neutral position. The sag of the oscillator is given as the resulting force F(pg) over its resulting stiffness K(pg) with pg gravity orientation. Then, if we want to cancel the sag, we must set to zero the resulting force caused by the external accelerations, which is gravity here. We found out that if we break down gravity into its x and y components, then it appears the resulting force has two main components linked to gravity orientation. So we have one term in front of a cosine and another one in front of a sine. Then, if you set to zero the resulting force Fpg, you have to set to zero the two coefficients A and B, which are in front of the cosine and sine terms. And this coefficient depends of the geometric and mass properties of the watt oscillator. So we gave in our paper the analytical solution for the resolution of these equations. Here we will show that one possible solution is to change the position of the center of mass of one lever, keeping the other unchanged. We chose here to change the one of the lever x1. In the figure on the right hand corner, you can see the displacement that has to be done with the counterweight of the lever x1 on the solid COMSOL model. Then we simulated the former and new configuration of the watt oscillator and showed that the sag passed to more than 150 microns to less than 3 microns. We can also see that our model is consistent with the simulation. For the stiffness variation, as the previous slide for the sag, we want to cancel out the gravity component. As the previous resultant force equation, the effect of gravity on the global stiffness of the watt oscillator breaks down into a sine and a cosine effect linked to gravity orientation Pg. These components are added to the natural stiffness of the oscillator that is due to its fluctuations. As before, we will set to zero this variation by cancelling out the coefficients C and D, which are before the sine and cosine terms. The solution of this new equation, coupled with the result of the previous slide, imposes on us only one real physical solution for the center of mass of the two levers. We can see on the right hand corner's figure the new imposed solution for the counterweights of the COMSOL watt oscillator. We simulated the previous and new configuration of the oscillator and see that the frequency variation changes from 170 mHz to less than 1 mHz. Again, we can see that our model is consistent with the simulation. So now, we just finished with the static balancing procedure. According to our model and simulations, the watt oscillator is quite insensitive to all in-plane linear acceleration. However, it is still dynamically unbalanced. The dynamic balancing in our planar study consists of cancelling the torques the oscillator is exporting to its frame while oscillating, as we cancelled the exported forces by statically balancing it. These exported torques are linked to the angular momentum sigma of the oscillator. Indeed, if we derive it with respect to time, you get what is called the dynamic moment of inertia of the oscillator, which represents the exported torques. So this angular momentum is composed of all the inertia and eccentric masses that compose our structure. And here we can see the greatest benefits of using a watt structure, because the two main levers rotate in opposite way, so their inertial terms are opposite, as you can see in the equation. So to cancel this angular momentum, we will have to correct the inertia of one of our levers without changing the location of its center of mass. Here we chose to adjust the inertia of the lever x2, and one can see the change that has to be done on the COMSOL watt oscillator here. Now, to catch the exported torque of our structure, we put it onto a frictionless free rotating stage, which is the big ring that you can see here around the oscillator. And when the oscillator will vibrate, as it is dynamically imbalanced, it will export torque to its frame and will actuate the rotating stage. To verify the effect of our balancing procedure, we will measure this angular motion. We can see that increasing the inertia of the lever X2 reduced by 5 the amplitude of the exported torques according to our simulation results. So finally, we have presented the procedure to balance statically and dynamically a planar watt oscillator. The structure now is then exporting no more force or torque to its frame, and it is insensitive to all linear and angular in-plane accelerations. Now we will briefly speak about its frequency tuning. So the frequency of a mass spring system is equal to the square root of its equivalent stiffness divided by its equivalent mass, all divided by 2p. The equivalent stiffness is the residual stiffness of the oscillator that we add at the end of our static balancing procedure, and the equivalent mass could be found writing down the kinetic energy of the structure. We can see that the inertia of the two levers have a main role in the equivalent mass equation. Therefore, by tuning them with respect to all the previous equations, we can adjust the final frequency of the watt oscillator. So, all the analytical results for the static balancing of the watt oscillator can be retrieved using an energy-based method. Our structure is composed of flexure joints and mass elements. Therefore, two kinds of potential are involved: the elastic one, which is noted VE, and the gravity one, VG. The elastic potential of our oscillator is the sum of 1/2 of the stiffness of the stressed flexure joint multiplied by the angular deformation squared, as there are only revolute joints in the watt structure. The gravitational potential is the work done against or with gravity to move the global center of mass of the watt oscillators above or below its original position. The total energy of our structure is the sum of the elastic and gravitational energy. Because our oscillator is 1 degree of freedom, if we derive this total energy with respect to its motion parameter, we will obtain the static force equation composed of the resulting force F phi g and the equivalent stiffness K phi g that we have found previously. Yet, we don't have to do all this calculation, as the important informations are hidden in the displacement of the global center of mass of the watt oscillator, the OG watt vector. The idea is to avoid any disturbances due to gravity. Then, the gravitational potential should be set constant or equal to 0 for all gravity orientation and for the whole range of motion of the oscillator. So to do that, the only solution is to fix the center of mass of the watt oscillator, making the OG watt vector constant. So to conclude this part, the A, B and CD coefficient that we had to set to 0 were actually linked to the first and second order displacement of the watt oscillator's center of mass along its x and y axis. So finally, we saw that we succeeded to model, simulate and balance, statically and dynamically, our 1 degree of freedom watt oscillator. So as this 1 degree of freedom oscillator is the basic element of our next 2 degrees of freedom oscillator, the same balancing procedure will be applied to it. The energy-based approach will be chosen for the continuation of our work. Indeed, it will be easier to model the kinematic of a structure, taking into account the parasitic motion of the flexure joints that will be used in the final oscillator design. We will also talk about the oscillator's isochronism default due to some second-order inertia phenomena that have not been discussed in this paper. Thank you for your attention. I wish you a good day.